Ever wondered how we separate valuable magnetic minerals from the rest of the rock? Well, today we're diving into the world of magnetic separators, especially two types that do all the heavy lifting in mining and mineral processing. Stay with us, because this is where science meets engineering magic. Magnetic separation is a physical separation technique used to extract magnetic or magnetically susceptible materials from a mixture of minerals. The basic idea is simple. It relies on the differences in magnetic properties between different mineral particles. In a typical mineral deposit, not all minerals respond the same way to a magnetic field. Some are strongly attracted, some only weakly, and others not at all. Magnetic separation uses this contrast to isolate valuable minerals from unwanted material or gangue. Let me break it down. Strongly magnetic minerals like magnetite are easily separated using low-intensity magnetic fields. Weakly magnetic minerals, such as hematite or ilmenite, require high-intensity or high-gradient magnetic separators. And finally, non-magnetic minerals like quartz, feldspar, or calcite are unaffected by magnetic fields and simply pass through. Magnetic separators can be categorized according to the intensity of the magnetic field in the medium. For weakly magnetic or paramagnetic minerals, high-intensity magnetic separators are used, while for strongly magnetic or ferromagnetic minerals, low-intensity magnetic separators are used. For coarser mineral particles, dry feed is widely used, and for fine or ultra-fine particles, wet feed is ideal. In magnetic separators, countercurrent and counterrotation mechanisms are two distinct ways of manipulating the flow of slurry and the rotation of the drum to achieve different separation goals. In countercurrent separators, the slurry, the mixture being separated, enters the separator at one end of the drum and flows in the opposite direction to the drum's rotation. The drum has alternating poles, north and south, that create a magnetic field. As the drum rotates, the magnetic field interacts with the magnetic particles in the slurry, attracting them to the drum's surface. The non-magnetic particles, tailings, flow out of the separator in the direction of the drum's rotation, typically through an overflow chute. The magnetic particles, concentrate, are carried around the drum by the magnetic field and discharged at the opposite end of the drum, where the magnetic field weakens. Countercurrent separators are often used for finishing operations on fine materials, as they can achieve high-grade concentrates with high recovery. Counterrotation separators, similar to countercurrent separators, use alternating poles to create a magnetic field, allowing slurry to flow in the same direction as the drum's rotation. They are commonly used in roughing operations for handling surges in feed and recovering coarse grain materials, but may not achieve clean concentrate. Magnetic separation is most famously used in the iron ore industry. Magnetite is a strongly magnetic mineral, so it can be easily recovered using low-intensity magnetic separators. Hematite, on the other hand, is only weakly magnetic. This requires high-intensity magnetic separation or high-gradient magnetic separation to recover it effectively. In coastal placer deposits and beach sands, magnetic separation is widely applied to recover heavy minerals. Ilmenite is moderately magnetic and can be separated using medium to high-intensity separators. Garnet is weakly magnetic, while rutile is typically non-magnetic. Here, magnetic separation helps pre-concentrate ilmenite before refining and separate non-magnetic rutile for further processing. In the processing of ores like wolframite, tungsten-bearing, and cassiterite, tin-bearing, magnetic separation is essential. Wolframite is weakly magnetic, so high-intensity magnetic separators are used to extract it from non-magnetic gangue. Tin ores often contain iron-bearing impurities or may be found in association with slightly magnetic minerals. Manganese ores like pyrolusite and pseudomelane often contain iron impurities. Magnetic separation is used to remove iron-bearing gangue minerals from manganese concentrates. In some cases, magnetic separation is also used to upgrade low-grade manganese ores if magnetic differences exist between phases. Phosphate ores often contain iron oxide contaminants, such as magnetite, hematite, or goethite. These impurities can reduce the quality of the final phosphate concentrate and affect downstream applications like fertilizer production. Magnetic separation is applied as a cleaning step to remove iron impurities, improving the product's chemical purity and market value. When evaluating any mineral processing technique today, it's essential to consider its environmental impact and energy demands. Magnetic separation, compared to many other beneficiation methods, has several eco-friendly advantages, but it's not without some trade-offs. Let's take a closer look. Wet magnetic separators, particularly those used in iron ore processing or beach sand recovery, require a continuous flow of water to transport slurry, remove gangue, and wash magnetic concentrates. While the water is often recycled, initial consumption and losses through evaporation or discharge can be considerable. This raises sustainability concerns in water-scarce regions, making closed-loop systems and water treatment increasingly important in modern plant designs. One of the strengths of magnetic separation is its relatively low energy consumption. Low-intensity separators used for magnetite, for example, consume minimal electricity. High-intensity and high-gradient magnetic separators do use more energy due to stronger magnetic fields, but advances in rare earth magnets and control systems have improved their energy efficiency significantly in recent years. Often, valuable minerals like magnetite, ilmenite, or even weakly magnetic iron oxides remain in tailings after initial processing. Magnetic separation allows these materials to be recovered from existing tailings, reducing the volume of waste and sometimes turning a waste stream into a revenue-generating resource. This not only improves resource efficiency, but also helps rehabilitate mine sites by reducing the load on tailings dams. Finally, a key environmental benefit of magnetic separation is that it is a non-chemical process. It doesn't use reagents or generate harmful byproducts. There are no emissions of toxic gases and no contamination of water or soil with processed chemicals. This gives magnetic separation a major edge over processes like acid leaching or froth flotation when it comes to sustainable mineral processing. Thanks for watching. If you found this video helpful, like, share, and subscribe for more content like this. And don't forget to hit the bell icon to stay updated with future videos. See you in the next one.